The third unit in the sets unit is on set operators, mostly union and intersection. So, first thing we want to define is what is the union of two sets and what is the intersection of two sets. So, the union, which is symbolized by U, so this reads as A union B. It is basically, and we use builder set notation here, X such that X is an element of A, and we use the connector OR, which you'll learn about more in the logic unit, or X is element in B. So basically, this is, if we're chasing elements, going back to that idea of chasing elements, then either X, if the element's going to be in a union, either has to be located in A or it can be located in B. It doesn't have to be in both. However, with the intersection, that is true. We use AND. So, upside down U is intersection. And I was always taught U union. The second letter in intersection is N. That kind of looks like an N. So A intersect B is where A is an X is an element of A, and I forgot my such that part. So going back, X such that X is an element of A, and X is an element of B. So the idea of and or is slightly different. I'm kind of getting a little ahead of the game here because logically we will talk about what the difference between or and is. And essentially it's kind of the same idea as with set notation. But, you know, if my two things were, if I said, I'm going to get, you know, if I say Friday, I'm going to go out to eat or go to the mall. Well, if I say or, I only have to do one of the two events. Doing one of them will be good enough, or I could do both. Now with and, if I say I'm going out to eat and I'm going to the mall, I have to do both actions. So with the intersection, it has to line both sets, basically, the elements that are in the intersection. So we'll do some examples. It'll make more sense, of course, when we do actual examples with elements in them, and we can chase the elements and work out the problem. So in this first example, A is actually the set 1 through 7. So 1, 2, 3, 4, 5, 6, 7. B is 4 4, 5, 6, 7, 8, 9. So those are my two sets. So my intersection would be, or actually let me start with the union. My bad. If we start with the union, it's everything, it's all the elements that lie in one set or the other set. It's set A or set B. So literally, you would basically chase down every element that appears in A or B. So it would be 1, 2 would be in there, 3 would be in there, 4 would be in there, because it only has to occur in one set. So 1, 2, 3, 4, 5, 6, 7 would be in there, and then those already repeat. You don't need to write them down. You would need to add 8 and 9. So let me rewrite that all in one line. So it's basically 1 through 9 is your answer. Now at the intersection, we are looking at the elements that lie in both A and B, which will be 4, 5, and 6, and 7. Those four elements lie in both A and B. So it's kind of almost like the overlap. And the union is almost like joining the two sets together as one and then, not writing down duplicates. But in any event, A union B would be just 4, 5, 6, and 7. And I'll pull that up here too. I'm hoping that this will be visible enough. I'm playing around some with the transfer to the computer, see how it comes out. But one thing, if it's not real good, the overhead slides, you can certainly pull up the slides off my D2L page when you're watching the videos. And then if there is something you're in doubt about, you can refer to the PowerPoint. So hopefully that will work. But in any event, there's your answers to those two sets. Okay. Let's let A be equal to A, B, C, D, E, F, B equal to A, C, E, C to D, E, and then D is A, B, C, D. So we're going to do A union B, A intersect B, A intersect C, and then C intersect B. So I'm just writing these sets down. So it's A is A, B, C, D, E, F. B is A, C, E. D is D, E. And then D is A, B, C, D. So we're going to do A union B. Let me get this out of the way so you don't be confused with the new one. So as you notice, though, a lot of these examples, I'll give you a collection of sets, and then we perform operations with the sets like we're doing here. That's a common theme in this sets chapter. But in any event, the union of A and B would be, if we chase down everything that occurs in one set or the other, it would be A's in there, B's in there, C's in there. You would also have D, E, and F. So you end up with A, B, C, D, E, F. Now one thing you'll notice, if you take union, and one of the sets is a subset of the other one, which it really is here, ACE is a subset of A, then it gets absorbed right into the union. So notice the union is the same as A, because B is a subset of A, and if you think about that, because of all the containment in B, all these elements lie here, this basically gets absorbed right into set A, in a sense. If we do the intersection, we'll discover that we have A in common, B in common, or excuse me, take that back. We have A in common, C in common, and E in common. So our intersection would be ACE. Again, taking the elements that lie in both sets A and B. A union C is basically, I'll just go through it. I think we kind of got the gist of this now. It would be, we're doing OR, so it's in one set or the other. So it would be A, B, C, D, E, and then F. And then the last one, the intersection of C and B is just the element E, it looks like. Yeah, because the only thing you have in common is E. So again, that would be your answer. All right, let me do this one as well. There are some things that come up in this one that are essential. I didn't really hit on everything, so let me run through this one. Typically, I try not to do duplicate ones, because I figure you can work those on your own. But this one, I think actually I will do. So if you do A intersects C, if you look and compare A and C, you're doing intersection. So it's and. So we're going to write down all the elements that occur in both A and C, which will be 3 and 7. That's it. If we do the union of those sets, you would, of course, do 3, 5, 7, and 9 from A. In addition, you would add 4 and I guess that's right. I really should have 9 in here. That's kind of interesting. I caught that mistake. But yes. Let me go back to that one, make sure I did it right. A, it would be 3, 7, and 9. So then the union would be 1, 3, 4, 5, 7, and 9. I think that's all. All the ones that got everything that's in A is 1, 3, 5, and 9. I'll double check. And then C would add additional elements, 4 and 7. Or just 4, I guess. Yes. Okay. I think I'll just keep this up here. C, the intersection of B and A would be just 4. So let's compare C to B. I said B and A, I meant to say C and A. Or I meant to say C and D. So intersection of C and D would be just 4. Yeah, because all the other elements are not common. Now here's the reason why I did this particular slide. It's this. A intersect B. Well, we compare those two sets. A is 1, 3, 5, 7, 9. B is 2, 4, 6, 8, 10. They have nothing in common. So your question is, what will be the answer? Of course, it will be the empty set, because it will be the set that has no elements. It's almost like, if you remember back to number systems, I may or may not mention this, but the civilization that came up with the concept of 0 was the Mayans. But the reason why that's so essential is, well, if you take 4 minus 4, well, now we have an answer to that question at 0. So, you know, before that, 0 didn't exist until people realized that, hey, if you take the number minus itself, what's the result? Well, you have to have something to account for 0, nothing. Well, the same thing is true in set theory. If you intersect two elements, two sets, and they have no common elements, the only way you can represent that is a set that has no elements, so therefore the empty set. So kind of much like 0, you now see we have this need for empty set. So questions E and F are interesting. If we take the set C, which is 3, 4, 7, 9, and intersect it with the empty set, well, there's no common elements because you're intersecting with the empty set, so the result's empty set. Think about it. So actually this is true for any sets. And I'll write that down as a rule in just a second. But if you take the set C, which is 2, 4, 7, 9 again, and union it with the empty set, you get 3, 4, 7, 9 back, which is C. I'll actually write that result. Because if you chase elements, you'll get 3, 4, 7, 9 by just picking out everything in C. And of course, that is C. So there's actually a rule here. That any set union with the empty set is the set back, A. And the set A intersected with the empty set is the empty set. Sorry about that. It's kind of interesting because what you're realizing is sets are taking on properties like numbers. I erase this part. But I mean, think about how with our number system, in our math, we have the concept of 0 and we have the number 0. But if we multiply any number by 0, we'll call it x, the result's 0, regardless of what that number is, right? Any number times 0 is 0. And any number plus this 0 is the number back. 4 plus 0 is 4. 5 plus 0 is 5. So this almost acts like a pseudo multiplication here and a pseudo addition, I'll call it. By the way, I won't get this deep on the theory on the test, but it's good to see that, one thing that if you do learn sets and set theory, a little set notation, is you'll see that there will be some properties that transfer over from algebra, which is kind of neat. But anyway, that's a little bit on union and intersection. Okay, example 4. And I'll actually write these down. Because I want to do a couple that are compound. So, if A is two, 3, 4, 5, 6, B is 2, 3, 4, 5, 6, 7, 8. And C is 3, 4. And I noticed I didn't even, I put D in the problem, but I actually didn't use it in any of the exercise, so I'm going to leave that off actually, because I really only need A, B, and C in this example. So part A, and I thought what I could do is do parts A and B, and I'll leave C where you can work it yourself and check it. But anyway, notice what I have, A union, parenthesis, B intersects C. Well, obviously I have two operations to work here. So this has to be done in 2 steps. The question is, what step do you do first? Well, your instincts would say, well, I remember learning from my algebra teacher that you always do what's in the parentheses first. And that's exactly what you do in set theory. So I'm going to recopy A. Let's write down the elements. And then union that with B intersects C. Now I'm actually going to perform this operation. So B intersects C, the common elements would be 3 and 4. So I've essentially rewritten this problem as A is 2, 4, 5, 6 union with, well, the result inside the parentheses is B intersect C is 3, 4. When we do the union, it's going to be, at this point, remember, it's you chase the elements, well, it's 2, it's 3, it's 4, and then 5 and 6. Okay, so in this one, notice the parentheses are around A union B, and then we're going to intersect C. So essentially, we're going to transfer over the parentheses and see what happens. So A union B would be the union of those two sets, which will be 2, 3, 4, 5, 6, and then add 7 and 8 from B. So the unions, everything in one set or the other set. Notice I use the word or. And then we're going to intersect that with 3, 4. Well, the only common elements, if we chase the elements down, are 3 and 4, because we are doing intersection. So that's 3, 4. And I'll try to always remember to step out of the way so you can see what I did. Again, common elements are 3, 4, because I probably am occasionally blocking the view. It's hard not to, working in such a small area. But yeah, any questions on that, please email me. So when parentheses are involved in a problem, much like algebra, do what's in the parentheses first when you're working out these set problems. Okay, like I said, I want to keep these videos a little bit short. I mostly want to work enough examples where at least you can see them physically worked out by hand. I'm hoping that will help. And then the other examples that are in the slides, that maybe you can work those on your own and check once you've kind of got the main idea down, which hopefully you guys do. I do want to do one example of a complement of a set. So, first of all, the definition of a complement of a set is basically this. The complement of a set A is a set of all elements in the universal set that are not elements of the set A. Now remember, I mentioned that universal set. That's the first time I've mentioned it since that first slide of the first section of this unit. So why do we need the universal set? Well, think about it this way. If you read the definition, it's saying that it's all the elements that are not of the set A. Or if you look at the builder set notation definition, the complement, which is, again, prime, A prime, prime means complement, is all the elements X such that X is not an element of A and X is an element of the universal set. And by the way, I apologize, I do use a slash. The colon and the slash have the same meaning. That's builder set notation. I don't care what you use, it's fine. So slash or a colon. Of course, Slash is the guitarist for Guns N' Roses. I had to make a joke at some point this semester. But anyway. So let's do an example where we're actually looking at some elements. So we're going to do A is actually the set 1, 2, 3, 4. B is the set 2, 4, 6, 8. And the universal set is every 1 through 9. So we're going to find the complement of A and the complement of B. And actually, you know what? You may not be able to see that. Let me move that over. I think I'm off. I bet you I'm off the camera. Let's see. I'll put it here. the complement of A prime, as we call it, is all the elements that are not in A that are in U. Well, if you think about this, A is 1, 2, 3, 4. And if we're going to attempt to do this little trick where we're saying, well, A is 1, 2, 3, 4, list me everything that's not in A, that can be a little bit confusing because what am I looking at? Well, if you have an index to draw from, which we do, the universal set, it makes a lot more sense. So basically you're saying, well, what is not in A? Well, you go to U and look, and then you pull out the elements that are not in A, which will be 5, 6, 7, 8, 9. So you can see, well, that's why we have the universal set. It provides kind of an index to draw from, or an index set, so to speak. It basically tells you everything you have to work with. So in this problem, we have the numbers 1 through 9 to work with. And it will change in every problem, by the way. So the universal set is not the same in every set. I don't want to say universal, never redundant. So the universal set will vary from problem to problem. In this particular problem, it's 1 through 9. It could be 1 through, or it could be 3, 4, 5, 6, 7 in the next problem. It's just something that's given to you. You don't have to worry about it. That is a set that will be provided, the universal set. So B, if we look at the set 2, 4, 6, 8, well, what's the complement? It will be 1, 3, 5, 7, and 9. Because that's everything that's not in B that lies in U. So basically, if you can imagine just pulling those elements out. So if we or you could remove. Another way to think about it is you could just take U and remove 2, 4, 6, and 8, and then what do you got? Well, you got 1, 3, 5, 7, and 9. So either way, you could think about plucking out the elements that aren't in B, or you can remove B from U, and that will give it to you. All right, so I'm hoping that will be sufficient, for complement. I will have problems again posted on the internet and out of the book for you to work. So that will conclude the units on sets. The only other unit is a brief one about the cardinality of the set, which is the last unit, and we'll talk about that in the next presentation. So again, email me if you have any questions, or go to. There's also other sources online. If you Google the particular topic, especially with sets, I'm sure you can find other sources. Hopefully. All right. Until the next time, we'll talk about cardinality.